right,
Yay.
you're up,
All right.
Andrew.
All right.
We'll
All
start
right. Forget
off.
use the browser. Okay. So this is back then. This is what we made. So we made this guy on the. I got there. They had this guy on the left. The guy in the middle is what we actually made with the fourth inside it, and it had these really impossible to use chiclet, keyboards. Um, Interestingly enough, I went to their website, and this is what they're selling today: a Windows program that you can customize data collection without programming. So apparently, the fourth didn't survive very long with there. All right, so after that, then I went to California, and I worked for Bill Ragsdale for a number of years at Dorado Systems. So the primary product when I was there was these magnetic stripe card readers for access control. They had a little 6805 processor in them. The processor, I did do a fourth on it, but it was really not satisfactory. There were 64 bytes of RAM, 4K or 8K of flash. It really was very tight. Most of the applications were written with assembly language with a fourth based tool set, right? So we used screens with fourth RPN assembly lumber in there, and that's how it was done. Um, I was also fairly, I don't know, fairly active. I was active in Fig and Formal back in those days. I went to the Silicon Valley meetings, and a lot of a lot of a lot of these names and faces are people who are still here. All right. So after that, what did I do? Okay. So then I went to Finnegan, which is now called Thermo Fisher Scientific, and they made mass spectrometers and gas chromatographs, other scientific instruments. So this is the product that we made. On the right hand side is the mass spectrometer. Um, Lots of really interesting stuff going on there. In the middle is a gas chromatograph. So basically, you put in your chemical for analysis. The gas chromatograph is a big long tube, and lighter things go faster, and so it spreads out what you're looking at over time. And the mass spectrometer then looks at it ionizes the compound and determines what was in it. Right, so you put your sample in there, and it says, okay, you've got X amount of this stuff in the sample. So on the left is the data system that is when I got there, the reason I was hired, they had a large fourth application um, running on MS-DOS that they wanted to port to Windows. So that was the task, to take kind of an F83 type Windows system and fourth system and get it running on Windows. So myself, Tom Zimmer, Andy Korzak, Bob Smith, there were some other people involved. Developed Win32 to solve this problem. We got permission from our employer to open source it, which was kind of nice. I basically did the internal stuff, kernel, compiler, the object system, and that. And then Tom did a lot of the editor and environment and stuff. He brought the FPC stuff in there. So it was a really fun time. Great, lots of stories about how it got built, and it's kind of interesting to see it still being used. I know Bill gave his talk on Win32. All right, so that's where I was, and then I left Forth. So in 2000, I left Forth professionally. I'd done a few hobby stuff, but this is what I did for the next 25 years. So I built these infotainment systems. Um, Interesting. We just had to talk about FPGAs. I'll just mention this for a second. So the system on the left, the upper one on the left, was a system we made for Chrysler. And inside it was a SH4 processor and a big FPGA. And this is some kind of Xilinx something or other, I don't remember, that was RAM based. So the SH4 would boot up, then it would boot up the FPGA, and it allowed us to have programmable hardware. So there was a common platform that we used on many different products that have different kinds of I/O, and so we were able to program the hardware for each one, right? So the SH4 was like the CPU and a memory bus. It had like no I/O at all. So it was an interesting combination there. All these other products I've done over the years, let's say no fourth. So now coming back to fourth. So what am I going to do, right? I retired this year, stopped programming professionally, and so okay, I want to do something fun. So what am I going to do? All right, so I play Wordle every day, and so I thought, why don't I see about writing a Wordle game in fourth? Um, so that's kind of the motivation for it, was to do something that was interesting. And so I'm gonna go really briefly through the game, and then talk a little bit about the algorithms for solving it, and and how far I got. There's the source code's published on GitHub. I'm going to show a little bit of the code. I don't know that I want to show a lot, but we'll see how it goes. All right. Any questions so far? All right. So I think. Go ahead.
GCMS that you worked on still being sold by Thermo Fisher, or do they
They
own
they
product replace the
that
Wordle?
particular product I don't think is, but they still sell GCMS systems. Yeah. Yeah, that was, yeah, I don't know if that's, I mean, I found, these pictures. I had to dig through I had to find these pictures somewhere. I don't, their current products aren't the same, I don't think, but
I suspect that Finnegan may have been bought to clear the way for their own product or a different division's product. Thermo Fisher has a long history of buying other companies. We used to meet at ABI, that they bought ABI.
yeah.
All right, sorry, go on.
Yeah, well, yeah, so I don't know. So after 2000, I don't know what happened to them. And they were Thermo Quest, or there was Thermo Electron, and it was all, they bought Finnegan right about when I was working there. Anyway, so let's just play Wordle. So this is the game from that's on the New York Times website. It originally was done by um, I forget the guy. Some guy in England did it on his own. He put up this website, and it became really popular. And so New York Times said, we want it. So you're probably familiar. So there's a 5-letter word you have to guess. And let me see if I can let me make sure I'm in the chat here. This is today's puzzle. Anybody, if somebody wants to guess a word, I'll take a suggestion. Otherwise, I'll type a fourth. All right.
Fourth.
All right. There's a good 5-letter word. All right. So this said that there are no F's, O, R's, or T, or H's in this. So we have to find another word that has some different letters. So it's going to score green when we get a letter in the right place, and yellow when we get one in the wrong
What's
place.
Ragsdale's favorite guess?
Patio.
Patio. All right. Even though I know there's no O, but I'll do it anyway. And there's no T, but that's okay. We're okay. Okay. None of those. We need some more letters like E's and stuff. I don't know. Cheap. I don't know what that is. Okay. There we go. We got a C now. All right. It starts with a C, and all these dark letters it doesn't have, and it has a bunch we haven't tried yet. Anybody want to guess?
Zebra.
Zebra.
Zebra doesn't have a C in it.
Oh, come on.
Yeah, well, it's
Oh.
okay. You don't have to guess word. Yeah,
Yeah.
they have this hard. They have this
Ouch.
hard.
Let's try to converge.
Yeah, we're getting way off base. So we're not going to get anywhere near this.
Lungs. Lungs.
Pardon me?
Lungs. Breathing. Lungs.
All right. Oh, look at that. Oh man, now we got all the letters. CLUNNG. All right.
C. All in the wrong place. Yeah.
Yeah, I happen to know that's the right answer because I played this game this morning. All right, so that's Wordle. All right, so now let's play it in fourth. All right, so
I guess I'd want to know.
Oh, come on.
What does that mean? Like the past tense of cling?
yeah, it's a terrible word. I clung. Yeah. Anyway. All right. So let's play a new game. So this isn't quite as slick, but I've got a new game picks a new random word. It's not clung probably. Anybody want to get? You want to guess fourth again? Or let's get fourth. Okay, so fourth gives us yellow R, and there's no F, H, O, and T, and so I'm kind of trying to reproduce what what this guy has on the left. All right, so how about another guess?
Rumble.
Pardon me?
Rumble.
Rumble. Rumbo?
Yeah. Bull. BL. Rumble.
ELE.
That's not.
It's not a word.
RUMBLE.
It's gotta be.
Well, that's too many letters, right? So if we do that, you need 5 letters. So
Girls.
girls, there we go. Okay, so now we got fourth and girls. So we got a R and an L. Now we know there's an L.
Zebra.
Zebra. You're gonna do that? Yes, zebra.
Pearl.
Who's that?
We know.
Pearl.
Pearl. Like that? Ooh, now we're getting closer. We got an L on the end and an R and E somewhere in here. So we should look at these unused letters here and, pick up, see if we can grab some of those. So what I do, okay, so let's see, R.
Maybe cheat.
Cheat. Oh, there we go. We got a C and an L, and there's an RE in there somewhere.
Create.
Ends with an L though. Ends with an L.
Yeah.
Cruel.
Let's try that.
Cruel.
Ah, damn, I got lucky. There we go. Cruel.
Cool.
Yeah.
All right, that was fun. Or maybe this wasn't fun.
Yeah,
Anyway,
what
that's the game.
That seemed like logical thing. It's cool. Yeah.
So.
Pardon me?
Oh, we were thinking what that was, and we said it before you put it out there. Cruel was it?
Yeah. All right. So that's basically the game, and it kind of plays like that. So if we could, there's lots of things we can do. So, let's see what we got here.
What's the monetization strategy?
You have to pay for every.
Too bad they don't pay you in Bitcoin for solving these things.
There we go. All right, I like that. All right, so we're okay. So I played the game. What else do I have here? All right, so there's 2 elements. There's 2 data types in the game. One is the words, right? So we've seen that there are these 5-letter words. There are the game actually has an embedded list of, this is the original game, there's more words now, but there's 13,000 words that you can use to guess from, but the solutions actually only come from this hidden word list of 2,300 words. I think there are about 3,000 something now, but so the other words you're allowed to use them as guesses because they might have more information in them than the actual words in there. So the process of solving is producing a guess, and we submit it to the game. We get the score, and then we use that score to reduce the number of words that we're considering. So I'm calling that the working set. So we start out with all 13,000 words, and we get a score, and every time we get a score, we reduce the number of working sets, so our problem becomes smaller. The goal, of course, is to get down to 1 by the time we get to the end of 6 guesses. And so there's the guessing part, there's the pruning, and then there's an end game strategy, which is there's some special cases at the end that the normal algorithms kind of don't handle well. We can talk about this in a little bit. Okay, so I'm going to show a little bit of code. This is basically the words are. I've created this big table of all the words. They happen to be sorted, although that's not. The program doesn't necessarily need to know that. So there's all the hidden words, and then there's followed by all these guess words. So there's 13,000 or so words in this array. so that my word WW, it takes a word number and produces an address. So we can in fact, it would probably be better to actually be able to type this stuff. So if we type word fourth, that's word number 795. So if I 795 and I print it out, it says fourth. Okay, so it's just the 795th entry in the table. And so the other part is a score. So for each letter you can have, for each position, you have 3 possible scores: a gray, meaning it's not there, yellow, or green. So there's 3 to the 5th total scores. So it's stored as a base 3 number, where you think about it like that. So each it uses 3 digits per position. I'm not saying this right. Okay, so we have, in the same way that we have word literals, we have score literals, and I don't know how this works. So if we take a word like a score like yellow, green, green, yellow, and so that's score 142. So 0 score is all greens. 242 is all greens. Sorry. So this number between 0 and 243 represents all the scores. And then the third bit of code is this working set. So the working set is just a linked list of words. It's kept in a separate array. And so we initialize it with all the words. So it basically puts all the words in this list. And as we prune it out, we take words out of the list until it gets small. That's this bottom word called prune here. I don't have the definition here because it's a whole screen full by itself. So this is how you iterate through the list. So this remaining is actually, it counts how many words are left in the working set. So it starts with 0, it takes the working set and it adds 1 to it, and it goes on until it's next. So this is kind of the basic iterator over the list, and different algorithms will do different things with each word in the list. Okay, and that's a snapshot of the code. Just all right, so there's 4 different guessing algorithms. So the first one is I call the simple guesser, and this is the one that is kind of the baseline because it's really dumb, but it's predictable. So it just takes the first word out of the working set. So it guesses a back and then gets some score and then guesses something else. It's interesting that it actually solves most of the puzzles because the pruning is actually what reduces the working set significantly. So the guess is actually less significant in reducing this 13,000 word set to something reasonable. So I have a random guesser that just picks a random word. Then the third thing I tried was a tally guesser. So I add up the letter frequencies. So I okay, out of all the words, how many of them have an E in the first letter? So more words maybe have an E than have a Q. So if you have an E, you get higher value. And so I just kind of added up each value. You have a lot of common letters, so you're a more important word. And that actually was not a bad algorithm. It worked better than random. And the last one I did, I ran across this wonderful YouTube video, and I will talk about it in a little bit, about using information theory and entropy to determine the value of a word, right? So different words have different amounts of information. So as we were guessing, each guess gives us some information back, right? And the guesses that give us a lot of information, like if I got a guess with all grays, that's a really lot of information. I've eliminated 5 letters, and I've probably eliminated 3/4 of the words in the dictionary right from that. Or if I get a word with a lot of greens, there's a lot of information there, right? I know these letters. So I'm looking for the words that have a lot of information, and that's what I'm going to guess with. All right. So here is the result. So this was the entropy guesser with the endgame strategy. It turns out that the entropy guesser actually doesn't need the endgame strategy. It's able to solve all of the puzzles in 6 or fewer guesses. with an average of 4.17. So the proven best way to play Wordle is about 3.4 guesses per word per puzzle, and you can solve all the puzzles in 5 guesses. So you can, I mean, there's only a finite number of Wordle games, right? You've got 13,000 words. You can guess 13,001. They each have a result. You could then take all the answers from that and try that. And so people have done that. They've written, large running computer programs that figure out what the best way to play Wordle is. And it's kind of a solved problem. I didn't do that because it seemed like almost like cheating. It's like, well, I'll just solve all the puzzles and then I'll find out what's the best word to start with. So what I did doesn't look that far into the game. So if we look at all the algorithms together, so these are the 4 algorithms, and this hidden is whether or not you know about this hidden word list. So if you know that there are only 2,315 words, then you have a lot of information that you'll use, especially later in the game. It's like, okay, well, I've got, why am I guessing these obscure words? I know they're not going to be the answer. So here shows the average and how many it failed. So they all fail except for the entropy guesser. So nobody, Tally got close with only 4 fails when it knew what the hidden word was, or what the hidden list is. But entropy guesser was actually able to solve it. Interestingly, when it knows what the hidden word list, it actually does more poorly. And the reason for that is the way the algorithm is written. I've got 2,300 words I could use to guess, but out of that 13,000, there's words in there that have more entropy, that have more information. And if I don't use those, I actually am hindering my ability to solve the game. All right, so I don't know how much I want to get into the entropy guesser. It's probably not worth getting into this here. It's probably, the code I have, as I say, I published the code in this link, and I think if we get here, we'll get bogged down into. Anyway, any question? Anybody want to look up more? Want to go in a different direction? We wrap it up, or what's the feeling here?
That's pretty cool.
I wouldn't mind you
I
diving
do have a
deeper into this.
question.
Okay, question.
Actually, my question is sort of a different subject. It's you used Lua in your and so I had identified. I've sort of been a language researcher, and I was searching for very small languages that were powerful, and Forth was one of my big choices, and but Lua was also a choice. So I thought, how hard would it be to implement Lua in Forth? And I was wondering if you know anything, if you have any thoughts on that.
Yeah, yeah. I don't think it would be very easy. I mean, Lua is a wonderful little language. We actually have it on one of the radios. I don't know about implementing it for. I'm kind of like, well, why? Because if you get done, then you've got Lua that's not quite Lua, but it's close to Lua. I'm not sure.
Well, if you're doing embedded Lua anyway.
Yeah, because Lua has it has a beautiful C, native C, their version of JNI, whatever it's called. The Lua virtual machine is beautifully done. If somebody's bored with Forth and they want to look at a cool language, Lua's like, I've stumbled on it, I don't know when, and I actually got to put it in a machine. So Forth we couldn't get anybody to buy into, but Lua, it looks kind of more like a normal language, but it's a beautiful thing. And it's interpreted. You can, and that's really nice. Anyway.
All right, you've answered my question. So back to the main
Yeah.
subject.
All right, so yeah, so I'm gonna I'll wrap up this Wordle thing here. So here's the end game strategy, and it's illustrated here. So you get to this, you've got 4 greens on guess number 4, but there's a bunch of words that fit there, right? And so if you just do your regular algorithm, you're just going to pick one of these at random. So you kind of get it. You say, okay, I've got, in this case, we have lover, mover, and rover. So I'll pick a word that has an L, an R, and an M in it, and it'll tell me which one of those is the letter, and then I can get to rover without having to just guess my way through it. Okay, so that was the fast tour of Wordle. It was a lot of fun. I I wrote it in Rust about halfway through. I thought, oh, does it look like in Rust? Because that's the last language I've been using at Amazon, and it was okay, but it wasn't nearly as fun. And what I missed was the interactivity, right? The ability to write a word and try it out, and that didn't work, right? Try something. That is magic when you're learning a new problem, right? So if you already know how to do this and you write it in Rust, which is where I was, right? I'd already solved it in fourth and it wasn't fun anymore, but the discovery was the fun, right? The other part that I unfortunately learned is that when I've got more than 2 stack items, it's really hard to juggle things around. And some of the algorithms with scoring, right? I've got a target word, I've got a guess word, I've got a score, I've got several things I'm working on at a time, and it's I'm getting too many dupes over and rotes in my code, and I come back 2 days later and I'm like, wow, I was so proud of this the other day and it works, but I don't understand what that is, right? And it would take me time to get back into it, right? So it's it's kind of it's not a right once, but it's along that kind of thing. Anyway, I had a lot of fun. I played Wordle better because I've learned more about how to get the most out of those first few guesses. My first guess is Salet, S-A-L-E-T, which is proven to be the best guess, right? The subtrees under there are the shortest, right? You want to get to the answer the quickest. And it's fun sharing. This is one of the things that I will miss about working professionally is sharing technology with people every day, right. So it's a constant collaboration thing. Hey, look what I did, it was cool. Hey, look what you did, it was cool. Hey, can we do something cool together? So I'm glad I got the opportunity to do that. I don't know what my next project will be, but I'll be glad to share it with you when I discover it. Any questions?
Just by idle curiosity, they say the model of your GCMS.
The model of the GCMS. Well, it was called the GCQ, and then it was called the Polaris Q. GCQ was the name that it was marketed under. Polaris Q will be there as well. I think that's what they called the gas chromatograph.
Yeah, you can still get parts for those. So they haven't vanished.
Yeah.
There's still people cranking samples through those.
Yeah. It was
episodes of CSI, I think.
Yeah, it's a fantastic, by far my most fun technically job, because I was working with PhD chemists and I was learning about chemistry while I was writing the software for them. It was a wonderful collaboration, right? You've got, they can't write software. I don't know chemistry, but together we're able to make a mass spectrometer. So yeah, there we go. I also worked on the mass spectrometer software, but that was in 58,000 DSP assembly code. So that had nothing to do with the fourth. The fourth stuff was on the data system side.
All right, Bob, ready to go?